Thank you all so much for joining Renew Risk webinar. I am going to hand over to Dickie Whitaker for a bit of an introduction, and then we'll be on to the Renew Risk team. So Dickie, over to you.
Patty, thank you very much, and welcome everybody. So I think I'd like to start by saying that when I started Oasis nearly 14 years ago, we had a few clear objectives. So one of them was to reduce the barriers to entry for new modelers, which would, by doing that, hopefully increase the choice for end users. And in addition to that, we were trying to stimulate innovation in a marketplace, which I think really had not seen that much innovation over sort of 30 plus years. And the team at Renew Risk, with the launch of these two new models, I think have exemplified some of the reasons why we did that 14 years ago. We've got real innovation here around particularly how you look at the vulnerability, which I would say is one of their key strengths, but also models that just cover perils and challenges that others have not seen fit to produce models in that space. So I think that's a fantastic opportunity for everybody on this call. I think practically there is one other important element that essentially Oasis and some of its partners brings to the table, and that is the ease of deployment. And we always felt very strongly that we should allow the end user to decide how they wanted models that were Oasis compatible to be deployed. And that means today, and in some cases this hasn't changed for a long time, but there are some new additions here, but it means you can have it on a laptop if you really want to. You can have it on your, on-prem on some servers. You can have it in every cloud you want. So the choice is yours, ultimately, about what makes sense for you and your business. But the latest two additions, as many of you will know, I think are significant. And they are through Model Exchange, you can now deploy any Oasis-based models into Verisk's new platform, Synergy Studio. And the latest addition was to produce Oasis Software as a Service Limited, which was designed primarily to serve the needs of Moody's users who wanted to deploy models through the, I think 2 or 3 year old now, IRP platform. So I think this really means that Oasis becomes a common standard in terms of modeling, in terms of exposure data, as well as some other things like how you can assess models and their viability, because you can get a model in just about any different format on any different platform you want. And there are some other ones that I could mention, but I think you sort of get the point. So I think it's exciting for you as end users to be able to see where Renew have gone in relatively short period of time. And I think the best thing I could do is hand over to them to introduce who's going to be talking to you today. So thank you very much, and over to you.
Thanks. I guess I can take control and start sharing, if that's okay.
Please do.
All right. So I guess thanks for the introduction, Dickie, and thanks for giving an overview of Oasis as well. We're happy to be part of the Oasis family, and launching these two new models is definitely showing how we can use the platform and use the framework and do our best with kind of the bringing these models into life. So I'll start we're 3 speakers today. I'll start to introduce myself, and then I'll ask my co-presenters to also introduce themselves. My name is George Descus. I'm the head of wind energy for Renew Risk. I joined the company about 9 months ago, and since I've seen the development of these two models. And before that, I was in research, working as an engineer and a principal scientist at NREL in the US. And one of the things that I'm really happy and proud today is that a lot of the research that has been done on this topic now kind of finds its way into model and kind of have to have practical applications. And with that, I'll pass to Ingrid.
Thanks, Yorgos. So I'm Ingrid. I'm the head of model delivery and innovation at Renew Risk. I've been at Renew Risk for a bit more than 3 years now and started mainly setting up the vulnerability modeling workflows and backbone of the vulnerability model. I was a vulnerability modeler at RMS. I've also had a brief stint into liability risk modeling and data science, which has expanded my horizon and my way of looking at complex problems and data. And I'm very happy that I've had the opportunity to bring some of that broad expertise to Renew Risk as in my role. I will now hand over to Raphael to introduce himself.
Thank you, Ingrid. Yeah, hi everyone. I'm Raphael. I'm an earth scientist by background and a CAD model developer for Renew Risk. I've been working in the CAD modeling industry for about 8 years now and spent the majority of my time at SCORE before Renew Risk in their CAD R&D team. And then, yeah, joined Renew about 3 years ago now, working as a CAD model developer focusing on the offshore wind perils. Thank you. Back to you, Orbis.
Yeah, thanks. So we have 3 parts today in our presentation, and what we'd like to do is to give an overview and do a deep dive of our model. And I would say that this kind of follows the launch of the 2 models, the EU and UK windstorm models. So the first thing I will do here is to try to give a little bit of a background about European windstorms and offshore wind. And maybe something that some people know, some people don't, but the offshore wind market in Europe is one of the largest in the world. It covers about approximately 45% of the global offshore wind installation, and you can see the rest is mainly in Asia. There's a little bit in North America, and that in terms of absolute capacity, we're talking about close to 39 gigawatts of installed capacity, and if you turn that into the total insured value, we're talking that's up, I would say, over 200 billion. So what you can see here is a map that's showing the different clusters we see that's mainly concentrated around the North Sea, the Baltic Sea, the Irish Sea, but as well as the Atlantic. And one of the things that we also know, or it's kind of the projection, is that we're in kind of on a track to get to even more offshore wind in the North Sea and the other regions I mentioned. And I think that the projected number is to go to at least 120 gigawatt of installed capacity by 2030. Now, what does it mean for us? It actually means that the market is kind of the way it's trending upwards. The insured values are growing rapidly, right? And that means that the offshore wind is kind of now becoming a portfolio relevant accumulation that we cannot ignore. It's not a niche class anymore. It's a kind of a systemic approach, exposure, sorry, that we have to deal with, and we have to think carefully about the different perils that we face in Europe. And speaking of which, I would say that the dominant peril is European windstorms. And this is not something new. And those who have worked in, commercial buildings and other exposures, they know that there have been, insured losses in the past. And I would say that in Europe, we'd see typically 5 to 10 significant events per season. And there have been also landmark storms like Lothar 1999, which caused billions in onshore insured losses. And hopefully back then, the offshore wind fleet was near zero. There was just only a few, like a handful of wind farms offshore, and therefore there were no reported damages. But today's 37 plus gigawatt fleet is kind of in a higher exposure region. And I would say that if you look at the 3 different pictures I put, this is Lothar, Anatol, and Daria, the wind farms actually exist where the wind resource is rich, obviously, because that's how you generate power, but also where the peril is. So it's actually one of the stormiest corridors on Earth. So that is something that we could potentially look at and kind of model with our existing models in a way. But there's also the question, and I'm trying to show here why offshore wind requires a dedicated model and why existing onshore property models weren't designed for marine assets. So I want to identify three main gaps here. The first is that the hazard that these existing models have is onshore only. That means there's no waves and there's no wind wave interaction. That a lot of times leads to underestimating actually the different hazards. The other gap is that vulnerability is generic. That means it's kind of proxy based. It's based on material, it's not based on the different mechanisms or the different, complex machines that we're putting out there in the open ocean. And the other thing is, of course, that exposure often is aggregated to single points, and it does not represent the expanded region that the wind farm may capture in the different asset types. And that leads to, when we use proxies to approximate, to approach these wind farms, we may systematically misrepresent offshore wind risk. And I'll just put here like a teaser that at the end, Rafael will show us a case study and we'll be able to demonstrate that. So what is the approach we take at Renew Risk? We take what we call an asset-first approach to offshore wind. The idea is that each asset has its own distinct failure modes and repair logistic and cost structure. That means that we actually need to model the actual engineering and not use a proxy. And the different assets we have, as you can see, here's like a mock-up, for example, of a wind farm, right? And what are the assets that it will consist of? We have wind turbine systems that includes both the upper structure, the turbine, if you want, the wind generator, and the foundation. We have cables, which are both inter-array connecting the different turbines together, as well as export. That means it takes the power and transports that to the land. And of course, there's some offshore substations that will, have to transform the voltage, and then obviously onshore substations. So all of these assets belong to the same wind farm, right? But they are so different if you look at them from their engineering. And I put here some pictures to just demonstrate that the failures are quite different, right? A blade failing is very different from a cable failing, and this needs to properly be captured. So I think Ingrid will talk more about that, and then she will have some examples from this. But there's one more thing that makes offshore wind quite different from everything else we have in terms of modeling, and this is the cost reality. And I want to just kind of draw attention to this fact that in offshore wind, the vessel mobilization is what dominates. So. And I'll say that offshore repair costs very often are driven by vessel mop-to-mop, not the materials, not the supply cost. And I give an example here that the minor blade repair, maybe you have to go in, inspect, maybe you have to kind of change a few screws there. It may cost the ballpark of about $30,000. But if you add offshore installation and maintenance vessel, the mobilization access, this can very easily turn into a 500K plus claim. And this is for a low claim. They might go to 10 million even. And we have seen these numbers in the market. And there's another fact, is like we don't have access all the time. There should be a good weather window that we have to wait for in order to be able to access a wind farm. And this waiting on weather delays can compound both on the cost for the repair cost, right? But also can compound the business interruption losses, because at the same time, the wind turbine that needs to be repaired is not going to be generating any power. So these are important things that one way or another need to be captured. So how does Renew Risk UK and European windstorm models address this gap? I'll say the first and foremost, we have generated a hazard which is a purely offshore hazard model, right? So we have 10,000 years of synthetic storms plus 65 years of historical. The model is fully calibrated to the observed offshore climatology. So that means we're using offshore data, both numerical data, let's say from ERA 5 and ERA 3, but as well as anemometer data where available. And then we also have a site-specific wind wave calibration. When it comes to exposure, we don't use aggregated, we use disaggregated exposure, and we're covering about 139 UK and EU wind farms, which include planned, under construction, and in operation. And the way we calculate exposure is through a bottom-up modeling, right? We actually take each asset specifically, we look at its classification, we look at its structure, and this is how we do the cost modeling. So there's a lot of kind of science that goes into doing this for exposure. Vulnerability, I'll say it's an asset-specific vulnerability curves for all types of coverage. I think Ingrid will go into detail. I'm not going to say anything more here. And the final thing, which comes to the last piece of a CAT model, which is the financial losses, we look at post-event loss amplification, for example, by explicitly considering mob-demob. This is what I said, that the $3,000 claim or $3,000 repair can end up being a $500K, like $500,000 claim. And obviously, when it comes to financial losses, there's the standard output like ground up loss, insured loss, etc. And so you can see that this is kind of happens in both models, both for the UK and the EU model. So I just want to kind of summarize here why this approach is different, and by just kind of juxtaposing here a little bit with the current market approach. So as I said, for exposure, often it's done in an aggregated fashion, usually even moved onshore. We all know this is kind of a common practice when we look at offshore wind. The renew risk approach, we do disaggregated and we'll look at the true offshore locations. When it comes to hazard, often we, the market approach is to take the wind only, that's the onshore proxy. We look at the wind and wave, calibrated both for offshore. Vulnerability, instead of generic property curves, we'll look at asset-specific fragility curves for all different assets. And finally, costs, instead of making onshore repair assumptions, we do offshore mob-to-mob, demand surge, and business interruption. And finally, I would say, and I think Dickie alluded a little bit to that, and I don't have here any pictures to show that there's kind of integrators with IRP, but this is a true, like a real Oasis model we're building, right? And we have full integration within the Oasis loss modeling framework, right? So it's a typical approach, and you can actually find the model either on the renew risk, what we call the green platform, as you can see here, or the various model exchange platform. Our models available in both. And the approach is very simple. It's like you upload exposure, you select the model, you run the analysis, you get the results. But to be able to do that, there are key integration points, right? So our inputs, they just follow the open exposure data format, and everybody can see what this looks like, right? There's specific codes, and this is kind of fully integrated. We're kind of following these standards, and kind of we're happy that this is kind of a transparent approach. The models, they're kind of available now. I'm not going to go into more details here, but I would say that both the inputs, the model selection, the outputs, they all follow Oasis loss modeling framework, and that is what makes it accessible and kind of ready to be deployed. And I think that's all I have, and I'll pass now to Ingrid.
You're still muted, Ingrid.
Thank you, Rafael. Thank you very much, Yorgos. Now what we're going to do is dive a little bit deeper into our vulnerability modeling approach, specifically why tailored vulnerability matters, which Yorgos already touched upon, but we're going to go a bit deeper into that, what our approach consists of, and what this actually delivers for the end user. So why does tailored vulnerability matter? Mainly because offshore wind assets are highly engineered and they do behave quite differently under extreme weather. So generic vulnerability assumptions typically wouldn't work, and they would heavily misrepresent damage and losses. So the way that we go about this, and again, Yorgos touched upon this, we take an asset level modeling approach across wind farm. We don't use just a generic one location wind farm code and location. We capture the key damage drivers for all of the assets in the form of what we call primary characteristics, and I will talk about that in more detail. And we apply advanced methods, modeling methods to obtain accurate results. So we use Monte Carlo simulations, statistically robust fitting, and a very granular cost model. The result of this is a set of hundreds of vulnerability functions that more realistically represent damage and therefore ultimately financial loss. So what are we modeling? We are modeling inside a wind farm at location level, specifically each asset. So we've got offshore wind turbines, we've got substations, both onshore and offshore. We've got cables, array export cables, and soon to come in our models, we'll also have interconnector cables. And for each of these assets, we consider the damageability of the assets in the form of their primary characteristics, so their key damage drivers. So for example, for a wind turbine, the age of the wind turbine, the capacity, the foundation type, and the depth at which it sits will change its vulnerability. I mean, age is quite an intuitive one. It's the same as property damage. Wear and tear and fatigue will obviously increase the vulnerability of the asset. But if we think about capacity, for example, it's a bit less intuitive. The capacity of the wind turbine will affect its size. So the larger the capacity, the larger the turbine. And therefore, this will yield higher loads on blades and tower, especially in severe weather conditions. So this is the reason why we consider these types of primary characteristics. If we look at cables, array cables, for example, have a small cross-section, they're quite flexible, and they're mechanically less robust than an export cable. So that's why we do need to model them separately. And then for all assets, we also consider things like the development stage, because wind farms that are fully operational offshore will have a vulnerability that will be significantly different from the disassembled parts, for example, of the wind turbines or the other assets in what we call the laydown area, which is the harbor where the assets are sitting before being dispatched and installed offshore. So we consider that aspect of things as well. So how do we go now about modeling these things? Well, the first stage is to obtain data, because obviously offshore wind farms historically are relatively new type of asset and exposure. There is not a lot of empirical data, so we do need to obtain data in the form of analytical data and expert elicitation. For the analytical data, we are closely partnering with the University of Surrey and Professor Bhattacharya's group, who are leading researchers in offshore wind turbine behavior and foundation dynamics. We can see here an animation of a wind turbine under wave load from one of the Monte Carlo simulations carried out. So these Monte Carlo simulations, essentially, they consist of running specialist software, so a finite element software called Abacus, thousands and thousands of times for a number of small variations of uncertain parameters, such as the nacelle mass and the diameter of the jacket legs, if we're looking at jacket type turbines. Things like the number of bracing systems, etc. So we vary these parameters to have some uncertainty and obtain a cloud of thousands of data points to which we can then fit a model. Where we lack data, we also partner with external collaboration partners. So we augment our data sets, for example, for cables, in partnership with a company called Cura Analytical. They are a Cambridge-based company focusing on subsea cable analysis. We also partnered with collaborators at SLPE. They are an engineering firm specializing in offshore wind structure design, and they've inputted a lot of important information on substations and foundation. So once we have this extensive data set, what do we do with it? So what we're trying to get first and foremost are what we call damage probabilities. So we need to understand how those offshore wind farm assets get damaged. In order to do that, we design a specific specific damage scale for offshore wind farm assets, which you see at the bottom of the screen. It starts from the lowest possible damage state, which is a remote start, and ends at the maximum damage state, which is an unrecoverable asset, so a complete write-off in insurance term. And what we do is we bucket the data that we've obtained in the previous step into those different damage states. And we fit to this data what we call fragility curves. So fragility curves gives you, that's what you see on the top left of the screen. They give you a probability of each of these damage states for each given assets and their primary characteristics as the hazard intensity measure increases, so as the severity of the hazard increases. This method is not just a generic method, it's a method that we have extensively validated and published in peer-reviewed journals. It was originally developed for tsunami damage estimations, and now we have adapted and applied it to the context of storm modeling for UK and Europe. So now we have damage probabilities. We still don't have vulnerability curves because what we need to use are the costs. So combining the damage probability with a sensible cost model is what allows us to obtain a suite of very specific to offshore wind farm vulnerability functions. So again, as Yorgos briefly mentioned earlier, we move away from generic cost assumptions and we build a detailed component-based model for offshore wind farms. So that model is, again, asset-specific and primary characteristic-specific, but it is also country-specific, and it breaks down the total cost structure into the essential components of the costs of repair or rebuild. So we consider and research separately labor costs, transportation costs, material costs, and other costs. So again, leveraging on Yorgos's point earlier, MOB and DMOD will be a huge cost, which needs to be considered separately from the other costs, and is something that maybe wouldn't be so much of a consideration in a more classic onshore property model. Transportation costs are the ones that are going to obviously be very important as well because of the vessel costs. So we combine all of this information. So we're going to have all of these costs for each of the damage states. We combine all of this information into a single curve using the damage probabilities obtained in the previous step, and we obtain our set of vulnerability curves. So why does it matter? So tailored vulnerability is not, I would say, it's not about adding detail for detail's sake. It's about making sure we are representing how each asset actually behaves under stress. The metaphor I often use for vulnerability or vulnerability functions is that they act as a dial that can be a very refined dial and that you can tune very well to represent the exact level of damage and the exact level of cost you will get for a given hazard. Or it could be a very rough dial that goes straight from 0 to 100 and doesn't actually capture the damage nuances that you need in the model. So by moving away from generic assumption and using more accurate information, essentially we get results that better reflect reality. We do that as well with PLA, post-loss amplification, which again we talked about this a little bit earlier, but PLA is an additional final calibration layer, if you will, that allows us to capture the specific behavior in wind farms where demobilization costs, mobilization costs are are much higher, but also things like the size of the wind farm will affect the overall cost of repairing one turbine or several turbines. So we do capture that as well as part of the vulnerability model. And this improves the loss realism and therefore financial decisions. So at this point, the key question is, how does all of this actually change the results in practice? There's vulnerability, but there's also exposure and hazard, for which we are taking a similar approach of detailed, accurate, and tailored modeling. So to explore the consequences of this modeling approach, I will hand over to Raphael, who will walk us through the case study.
Thank you, Ingrid, for that quick intro. Okay, now we move on to the next slide. All right. So yeah, thank you, Yorgos and Ingrid, both for your parts. In that last section of our webinar today, I will try to tie up all of that information or tie it together with the case study and take more the perspective of, say, a CAT model or an underwriter. And that case study uses a real-world pricing example to highlight how leveraging our newly released UK or EU windstorm models in the correct way can improve your offshore wind risk decisions. So imagine you receive a submission for a typical offshore wind farm located somewhere in the North Sea. You might have limited exposure information available, probably a tight deadline to work with, and you still need to somehow come up with a confident pricing and risk decision. And depending on how you model that risk, you can arrive at very different conclusions at the end. So for that case study here, let's assume two different approaches. The first one is what we call the proxy-based modeling approach, and it's a very pragmatic way and simplified way of representing the risk. And you are just aggregating your exposure information into a single location, move it onshore, and you just apply a proxy vulnerability curve. And then the second approach will be the purpose-built offshore modeling approach. So, for example, using one of our models with detailed exposure data, where you're capturing the full hazard spectrum and you're also using component level or vulnerability functions. And both approaches here are aiming to answer the same question, but they rely on very different assumptions. And to better understand the assumptions, I've broken that information down step by step in the following slides. And we will start by looking at the differences in exposure information, because everything begins with how you represent your risk in a CAT model. So before we even move on to, or before we consider the hazard and the vulnerability, we can see that the way we represent the exposure data already has a significant impact on the outcome. And as I've said before, in our proxy approach, we're combining or aggregating all wind farm components into a single location, move it to the closest location onshore. And that might be a pragmatic way or a quick way of modeling that, but in reality, it ignores the turbine layout and the spatial spread. So it also misrepresents where and how the losses could actually occur. And in the second, the purpose-built modeling approach, we're considering very detailed exposure data. So in that case of the scenario here, we take our offshore wind farm in the North Sea. That's represented by 88 individual turbines, the blue triangles here in the map. Those turbines are connected to the land with here in this case, two export cables. They're broken down into individual segments. It's the gray dots or lines connecting the turbines to the land. We've got two offshore substations. We've got two onshore substations. And we also have the infield cables represented individually connecting the turbines. And in this approach, we're capturing the true locations of every single asset, and it's exactly how exposure data will be represented in Renewables industry exposure database, where we have that detailed information or exposure information for all offshore wind farms globally within our model domains. So now that we've seen that difference in the exposure representation, we can move on to the next layer, and that will be the hazard, specifically how the different hazard forces are captured in the two different approaches. So once we move on to the hazard from the exposure, we see that the differences become even more pronounced. For all of our offshore wind models globally, we are explicitly capturing wind and wave impacts on the offshore structures. And to do that, we've partnered with the Danish Hydraulic Institute, the DHI. It's a leading engineering firm specializing in oceanographic modeling and offshore wind conditions. And what you're seeing here is an animation from DHI. It's actually for a different region, but it's just for illustrative purposes because the underlying methodology is very similar for UK and EU windstorm models. And what you see on the right side is just a wind field of a sample storm moving towards the land. And on the left side, you see the corresponding simulated significant wave heights for that wind field. So using DHI's in-house wave models, they can simulate how a wind field translates into wave conditions, capturing both the significant wave height and also the wave period. And with that information, we can then derive consistent statistical relationships between wind and wave behavior across the whole model domain. And in the last step of our hazard methodology, we then combine the simulated wind speeds, the calculated wave heights and wave periods into a single intensity measure for the CAD model to properly link the hazard and the vulnerability modules. And that single intensity measure in our offshore wind models is called the ocean energy. So that fully captures the hazard impacts on offshore wind structures. And like I've said before, in the proxy approach, we're only considering on-land wind speeds here, and we're completely ignoring the wave impacts. But we know that windstorms behave differently offshore, and both the wind and the wave become important drivers of potential damage. And in the first chart that we see here, that's showing the wind hazard curve for the two different exposure representations. And we see that they're actually broadly similar, with the onshore wind hazard being slightly below the true offshore location. But the key difference that I wanted to show here is the zero wave hazard curve for the proxy approach. And that obviously then translates into our model intensity measure in the total ocean energy curve, where we see a significant gap between the proxy and the purpose-built modeling approach. So at this stage, we are already feeding a fundamentally different hazard into the model run. And then the next question is, how do the different damage hazard forces translate into damage? For that, we look at the vulnerability. And in the proxy approach, we're aggregating all components into a single location. So that means we also have to map that location to a single vulnerability curve. If you're using one of our offshore wind models, you would most likely use the turbine or code that location as a turbine. But the problem is that you're assuming a uniform damage response across all wind farm components here, and you're not reflecting the offshore specific failure mechanisms. But just like Ingrid and Yorgos have highlighted before, the different wind farm components, they respond very differently to the offshore windstorm hazard, specifically where the wave becomes an important driver of damage as well. And in our purpose-built modeling approach, we then have component-specific vulnerability functions in our model. So every curve here could represent a different kind of a turbine or cable. And the key benefit of using those curves is that every curve reflects the correct construction type and failure mode. It captures the combined wind and wave-driven damage mechanisms, and is also calibrated specifically for that asset type. So now that if we combine the differences in the exposure representation, the hazard impacts, and the vulnerability functions, what does that mean in terms of model losses? As expected, we see quite a big difference in the model losses for both approaches. With the proxy approach, here I'm showing the annual average loss in the first chart being about 60% lower than the purpose-built modeling approach. And that difference in model losses becomes even more significant in the tail. Here, as a second example, I'm showing the 1 in 250 OAP loss. where the losses are about 90% lower under the simplified scenario. And another benefit of using the purpose-built modeling approach is that you could also break your losses down by component to get a better insight into the different drivers of loss. And here in the bottom, it's the bottom left chart. I'm showing the annual average loss again, broken down by component for the purpose-built modeling approach. So if your view of losses changes like that, it inevitably changes how you price, manage, and structure your offshore wind farm risk as well. And using the purpose-built modeling approach with highly detailed exposure information, you will have a much better overview of your potential losses and ideally be able to make more informed and confident decisions across your business. Before we wrap up with that case study, I would like to show one counterintuitive example as well. And in that example, we basically keep the same assumptions as we have in the proxy approach A previously. So we're aggregating all components into a single location again, but instead of moving it onshore, we move it offshore to where the turbines are located of that wind farm. And in that scenario now, we're capturing both wind and wave impacts, but we're still relying on the single simplified vulnerability curve. And again, we use the turbine vulnerability curve here to be consistent with the previous approach. But in terms of property damage losses, the turbine is actually the most damage sensitive component across all wind farm components. And that means that in this approach now, the results actually flip, with the proxy approach being about 50% higher in the AAL compared to the purpose-built modeling approach, and about 40% higher in the tail. So you can see that with only a very small change in your underlying assumptions, the losses can swing quite a lot from being materially understated to overstated. And that just highlights that they are very sensitive to the assumptions you're making, and they can very easily misrepresent your offshore wind farm risk. So that was it for the case study. I hope it was insightful and helped to illustrate that the way we model offshore wind risk makes a real difference. All of the different components, the hazard, the vulnerability, the way we represent the exposure data, they all matter. And using the purpose-built models, such as the ones that we just released to the market, they will help you to make more informed and better decisions across your offshore wind risk business. And if you're interested in that kind of content, we are also publishing, or we are working on a white paper at the moment that will be published soon, providing a bit more information on that methodology, probably a few more case studies. So yeah, if you're interested, make sure you subscribe to our newsletter or check our website or the LinkedIn page. And I think I quickly hand it back to Yorgos for some closing words before we move on to any potential questions.
Thank you, Raphael. Okay, so let me go to our conclusions. So I guess I think the Raphael's case study was really, really enlightening, but I want to kind of bring back everything into kind of where we started. And I want to say that offshore wind now, and particularly in Europe, is a portfolio relevant accumulation, right? We have 39 gigawatt of installed capacity in Europe today that comes up to more than 200 billion of insured value, and it's growing at 90% of like every year, right? This is the annual growth rate. That means that the risk can no longer be approximated. We need models that can really kind of break down the different assets into kind of their own vulnerabilities and look at them holistically and kind of do it properly. The other thing I think, and that was kind of for me at least, that was the main takeaway from the case study, is that yes, you can use proxy approaches, but you're going to systematically misrepresent offshore wind losses. And what the case studies showed, particularly adding the counterintuitive example in the end, is like, depending on the assumptions you make, right, the loss can be 60 to 90% lower or 40 to 50% higher. To me, that means that this is not a conservative approach. It's just the error is unpredictable. right? So you have to do it properly. You have to do it in a way that you take every single asset into account. And to do that, I think I would say every layer of the model matters. I think what we demonstrated here today is that the exposure granularity matters, offshore hazard matters. You need both the wind and the wave to be able to model that. And you also need the asset-specific vulnerability together with the realistic, say, cost modeling, right? Repair cost with mob-demob, with accessibility, with everything. And this is kind of where the purpose, what we call purpose-built modeling, enables better decisions, because you can do more accurate pricing. There's a clear aggregation views, and there are kind of more confidence, greater confidence in both the reinsurance terms and the capital allocation. And I'll say the final thing, and I want to kind of leave everybody with this, is that this model is fully integrated with the Oasis loss modeling framework, and that's why we're here, kind of hosted by Dicky and Oasis to be doing this, because we're using all the native tools that kind of Oasis offering, and we're using the same standard inputs and outputs, and that makes it easier. That makes it kind of a workflow enabled model, or enabling model, I would say. And with that, I'll just stop here, and I guess back to you, Dicky, and to kind of, I think the next thing we have is questions. So I'll go back to you, Dicky, or Jess, to let me know if there are any questions from the audience.
So just stick your hands up if people want to do that. Jess, do you want to? I can't see the questions actually on my screen, so.
Yeah, I can do that. There's a question for Ingrid, I think is the best person to answer, from Remy, which says, as opposed to most onshore facilities, which are usually not designed for detailed site-specific evaluations of the environment, offshore wind farms are designed with very detailed engineering, including position-specific loads and damages, and highly accurate metocean assessments. This certified documentation is usually available from the project owner. Can you make use of this in your model?
Yes, thank you, Remy, for the question. So we have already actually done that in one of our other models. So in the Japan TC model that we've released, we have taken into account more granular information on the different on the site-specific information, and captured that through another primary characteristic that we call vulnerability regions. We are actively in the process of thinking about how to implement that in our Europe and UK model as well, but that's a very good point, and we are definitely thinking about doing that and looking into this.
Thanks, Ingrid. And I suppose one for Raphael about your case studies, which says, to clarify, do both approaches B and C assume variation in cost of failure for similar asset classes?
Sorry, I'm not seeing that question. Can you say that again?
Yeah, it says, to clarify, do both approaches B and C assume variation in cost of failure for similar asset classes, i.e. an IAC carrying 1 times WTG capacity versus an IAC carrying 5 times WTG capacity?
Thank you for posting that. I'm a bit just trying to read that one more time, sorry.
Can I just...
you can also jump in, Yorgos.
Yeah,
just trying to
I would say that the approach that was taken in B is the one where explicitly each asset was modeled. That means that there was like turbines represented by turbine vulnerability, cables represented by cables vulnerability. I think in approach A and C, everything was approximated by a kind of turbine vulnerability function, right? So I think in terms of the costing, maybe, but in terms of and that's kind of the point. In terms of the vulnerability, they weren't, because it was all approximated using a single vulnerability function.
Yeah. Thank you, Yorgos. That's correct. I'm not Sorry, I was first a bit confused when I heard that question, but yeah, there's no differences in the wattage capacity assumptions for the proxy approaches because we are just using the simplified turbine vulnerability curve and assumptions.
Thank you. And Yorgos, one for you about evolving technology. So with offshore wind technology continuing to evolve rapidly, how often do you propose to review the model assumptions behind the offshore models?
Yeah, I would say there are different aspects of the model may need to be reviewed differently and more often. I would say when it comes to exposure, we see, and I showed the chart which shows the growth in Europe, right? So that means next year, in 2 years, the exposure will probably have reached 50 gigawatt or like 100 gigawatt, right? So that will need to be reviewed. Some wind farms will be decommissioned, new builds will be kind of commissioned, and that means that exposure part will need to be updated. I think also the vulnerability will need to be updated. As you know, a 3 megawatt turbine behaves very differently compared to a 20 megawatt wind turbine. So there are different generations of turbines in the water. I think what we need to do is we need to update that, and that can also happen in a kind of like a year, every year or every 2 years when it comes to vulnerability. The final thing I would say is that something we're kind of also very keen to find out is how hazard is evolving, which is, what is the effect, for example, of climate change? Do we see more, do we see more severe windstorms? That's something that we'll need. So for a offshore wind model, all 3 components will need to be updated on a regular basis. I think some of them more frequently than others.
Great, thank you. Another question, I don't know who wants to jump in on this, but it's how would you envision aggregating this model's losses for offshore wind assets with onshore property portfolios that are modelled with a different vendor? Can the event set be extracted and compared for event comparison?
Can the event set be extracted? I know.
Well, can I maybe have a little go at this one? So there's a couple of things. So one is that you can obviously, as in every model in Oasis, you can extract the event sets and you can do what you want with those event sets afterwards in various other software packages. So that bit's easy. The second thing is when you've got comparison of results, or we have an open results standard, that we are increasingly talking about how we can use this as a functional method in the marketplace to do exactly that, because there are techniques that are out there to be able to compare event sets for correlating or even non-correlating actually perils. So that's the sort of short answer. Matthew Jones, who's on this call from Oasis, is actually talking about this at our conference in 2 weeks' time on a panel a little bit. Matt, if you're still there, because I can't see, anything you'd want to add, putting you on the spot, or should we just get people to go to the conference? That would be easy. Maybe Matt isn't, because I can't see actually. Thought he was earlier on. Anyway, the short answer is there are ways of doing this, and if that person wants to get in contact with me, I can give them a paper. I think that they've, or me or Harriet, we can give them a paper that talks about this a bit.
Thanks, Dickie. A question for Ingrid about how we handle the risk modelling of assets that are often still in construction.
Yeah, so yes, thank you, Mattis. So we have a primary characteristic for assets in construction in our schema. At the moment, we are developing the vulnerability curves for that. So the only thing that's available as of today is laydown and in operation. So as a proxy, we use operations in operation, but under construction is definitely something that we are adding to our models.
Thanks, Ingrid. And Raphael, can you explain a bit more about what role Oasis plays here?
Mm-hmm. Yeah, I think Yorgos tried to mention that earlier already. Oasis basically we've developed our model within the Oasis loss modeling framework, and you can imagine it as the financial engine of your CAT model, where all of the other components of the CAT model we are developing ourselves. So the hazard, the vulnerability, and the exposure data. But the financial engine for every Oasis model is uniform, right? And that's one of the core ideas of Oasis as well. And you would get the standard Oasis loss modeling outputs that you would get from any other Oasis model. Yeah, that's the role that Oasis plays in our CAT model.
I would say one more thing I'll add here, that we also use the open exposure data and the exposure standards as well, which actually makes it very, very transparent and kind of gives a lot of visibility to people how they need to build their we obviously have our own ID, which we kind of recommend everybody kind of using, because this is what we kind of spend a lot of time and effort in building. But having both inputs and the outputs, kind of being have clear standards and can be easily read and can be easily understood, that actually kind of a great point where we like integration with Oasis, and that kind of gives kind of propels our model to kind of increase usability.
Nice. And Yorgos, you mentioned the industry exposure database, the IED. Francesca's asked for a bit more information on it. Is it based on our existing farms, our assumptions, a hybrid? What's it built on?
So we collect information and data from different sources. Obviously, for the existing wind farms, we have exact layouts and that kind of both the turbine rating and the location, everything is exact. When it comes to future under construction, we use as much of the publicly available information, and then we build on some of our assumptions. But I would say overall, even for future wind farms, they're fully validated using kind of information we can get from some of our kind of, for example, early evaluators. So I would say the idea is a hybrid approach. When it comes to existing wind farms, it's 100% accurate in terms of the of the locations and the construction types and everything. When it comes to future wind farms, there's a little bit of kind of guesswork, but this is kind of, I would say, very limited. And as more information becomes online and available, then we very quickly incorporate that.